necessary and sufficient conditions should be satisfied to be transformed as Fourier transformation, Fourier transformed expression. And that is very much similar to the Dirichlet condition, except one thing is that the function or the signal that should be absolutely integrable. Absolutely integrable in the sense, if we take the absolute value of the function and take the integral over minus infinity plus infinity, and if we get the finite value, if we calculate this mathematics, and if we get the finite value of this particular integral, then we can say that the function is absolutely integrable. Okay, this is the condition, so that the function could be expressed as Fourier transform expression. Okay, so let me present the PDF. So Fourier transform here, xt to x omega this unit step function here. Okay, so here we were in the previous class. So Fourier transform. Okay, so yes, a Fourier transform of bound signal, and we have talked about the unit impulse signal delta t, Fourier transform one, and then we have discussed on the exponential function e to the power minus at, which is exponentially decreased in nature, into ut, where ut is the unit step signal. And here we have found that the Fourier transformation of this exponential decreasing function is 1 by a plus j omega. 1 by a plus j omega, which is very much equivalent to your Laplace transformation by setting up s is equal to j omega. Okay, this can be happened only because the function, exponential function, is absolutely integrable. Okay, so this is why we can set up s is equal to j omega to obtain the Fourier transform. Okay, Fourier transform in terms of j omega term, and that is 1 by a plus j omega. This is the Fourier transformation of the exponential function e to the power minus at ut. Okay, so this is the thing. Okay, now come to the exception. This is what we have to look into very carefully. The Fourier transformation of unit step signal. So let me convert it into full screen mode. Exponential, yeah, this is unit step. Actually, unit step signal is not absolutely integrable in nature. Why? Because if we take the integral over unit step using the lower limit minus infinity and upper limit plus infinity, then we will get the infinite value. Okay, that will not provide the finite value indeed. So basically, if we talk about unit step can be defined as ut is equal to 1 for t is greater than 0 and is equal to 0 elsewhere. I mean, is equal to 0 when t is less than 0. So the limiting value will be transformed from minus infinity to plus infinity to 0 to infinity. Okay, as the function is defined over 0 to infinity, this interval. So this is why the limiting value has been transformed from minus infinity to plus infinity to 0 to infinity. And if we take the integral over 0 to infinity for unit step or 1, you can say that will provide the infinite value, that will not provide you the finite value. This is why we can say the unit step signal is not absolutely integrable at all. Okay, so we cannot get the Fourier transformation according to the rules and regulation, right? So, but this is an exception, but we can get the Fourier transform of unit step response or unit step signal, you can say, and we will see the proof also how we can get the Fourier transformation of unit step signal.
এটা কি 0 প্লাস থেকে নেওয়া হচ্ছে না 0 থেকেই নেওয়া হচ্ছে?
0 to infinity, okay?
Okay.
But yes, one thing is to be noted. This is a good question actually. What you are saying 0 plus to infinity, right? Yes, actually, in practical sense, yes, theoretically it is correct that we write ut is equal to 1 for t greater than or is equal to 0. I mean 0 has been included. But in practical sense, at the point t is equal to 0, the step response is undefined. Okay, so in practical sense, it should be 0 plus to infinity. What you are saying?
Okay.
Not clear. But because at the point t is equal to 0, the step response is undefined in nature in practical sense. Because at t is equal to 0, there cannot be two values, 0 or 1, right? But you can say, if we recall the Fourier series, then we may say this is piecewise discontinuous, and at t is equal to 0, the value converges to half. Actually, at t is equal to, I mean,
yes.
I think understand is better. I mean,
average
t is equal to 0 minus and t is equal to 0 plus by 2. I mean, that is 1 by 2. 1 plus 0 by 2, that is half. Actually, at t is equal to 0 point, the functional value converges to half. This is the in case of practical sense. But yes, in many more textbooks also, you will see the unit step signal is defined as 1 for t is greater than or is equal to 0. But this is theoretically, actually, we can write. But in practical sense, we can say ut is equal to 1 for t only greater than 0, not equal to, greater than 0. And at t is equal to 0 point, the unit step response, the unit step signal is undefined in nature. Okay, this is the thing.
Sir,
now I think yes. Yes. Any question? Okay. Okay, I think now it's clear to you, right?
Yes, sir.
Okay, thank you. Yes, and pardon. Yes, and if we talk about the Laplace transformation, the Laplace transformation of unit step signal is 1 by s. Okay, and the region of convergence is a real part of S is greater than 0. Okay, this is the thing. Actually, if we read about the Laplace transformation, then we will see the Laplace transformation of unit step signal is 1 by S. Okay, that means the Laplace transformation exists 1 by S. Okay, and without any kind of exception or without any kind of vegetation, we can write the Laplace transformation of unit step signal is 1 by S. Okay, and we can also prove that using the definition of Laplace transformation, which is integration 0 to infinity ut into e to the power minus st dt. Okay, if we calculate this sum or this mathematics, then we will see the Laplace transformation of the unit step signal is 1 by s. But when we are going to obtain the Fourier transformation of unit step signal, then we are facing some problems actually, as because the step signal is not absolutely integrable. Okay, this is the thing. But I mean, we can prove also, and we can see the unit step, the Fourier transformation of unit step signal will be obtained. Okay, will be obtained, and the we will see the proof also. Okay, in my further discussion or in my further class. Okay, so now let's come to the point. Yes, the Fourier transformation of unit step signal is pi delta omega plus 1 by j omega. Okay, which is not obtained by keeping s is equal to j omega. Okay, if we talk about this thing 1 by s, the Laplace transformation of the unit step signal is 1 by s. If we replace the s by j omega, then we will get 1 by j omega, right? So 1 by j omega is retaining here, but the additional term is pi delta omega. How it will come, we will see it further. In our further discussion, we will see how we can get the Fourier transformation of ut as pi delta omega plus 1 by j omega. Okay, we will see it further lecture, and just be patient. We will see it later in further discussion how we can obtain the Fourier transformation of the unit step signal, that is pi delta omega plus 1 by j omega. Okay. So 1 by j omega is fine. This is retaining as same as the Laplace transformation if we set the s by j omega. But what about the Dirac function, the Dirac delta function, pi into delta omega? What about this Dirac delta function? We will see it later in our next class or in our next lecture how it will come. Is it visible to everyone?
Yes, sir.
Yes.
Okay, thank you. Yes, yes. So now come to the another property, which is linearity. I mean, linearity of the Fourier transformation. Let's take two individual signal. One is x1t and another one is x2t. And the Fourier transformation of x1t is x1 omega and x2t is x2 omega. If these two conditions is satisfied, or if this statement holds properly, then a1 x1t plus a2 x2t, if we take the Fourier transformation of this combined signal, then we will get a1 x1 omega plus a2 x2 omega. This is very easy and simple thing. This is the linearity property of the Fourier transformation, and you can prove this easily. Now come to the time shifting property. Time shifting property. I mean, here the Fourier transformation of xt is capital X of omega, and the inverse Fourier transform of x omega is xt, right? And time shift, I mean, time is being shifted. That may be forward or maybe backward. But here we have taken the backward shift, x of t minus t0. I mean, in case of your present scenario, that was xt, and if we shift the time backward t0 time, then we'll get what? T minus t0. That is delay. Obviously, this is called delay also. So let's take the Fourier transformation of this delayed signal is x tilde omega. X tilde omega. So now we are going to calculate what is the expression or what is the formulation of this x tilde omega. Okay. Okay, let's see how we will get the x tilde omega, or we will see what happens in case of your frequency response if we shift the time backward in time domain. Okay, so our objective in this time shifting property is if we shift backward the time, or if we delay the signal, what would be the frequency response, or what change will happen in the frequency response, or in case of your Fourier domain. Okay, we will see it. Okay, so yes, that is equal to minus infinity to plus infinity. Is the simple definition, you know. So x of t minus t0 e to the power minus j omega t dt is the simple Fourier transform definition. And if we take, or if we imagine t minus t0 is equal to t tilde, if t minus t0 is equal to t tilde, then dt is equal to d tilde, right? This is simple integration. Actually, this is simple differential. Actually, if we take differential for the both sides, then we will get dt is equal to d tilde. Now we substitute x of t minus t tilde by x of t tilde as t minus t0 is equal to t tilde into e to the power minus j omega t tilde plus t0 d t tilde, right? And finally we will get x of t tilde e to the power minus j omega t tilde d tilde into e to the power minus j omega t0, right? So and this whole expression x t tilde e to the power minus j omega t tilde d tilde, this whole expression represents capital X omega, right? Because capital X omega, that is equal to integration minus infinity plus infinity xt to the minus j omega t dt, right? So whatever may be the variable t or t tilde, the final integral would be remain same, and that is capital X of omega. Okay, and that is remained intact, e to the power minus j omega t0, and that will be remained intact. So e to the power minus j omega t0 into capital X of omega. So finally, if we shift the time backward by t0, then we will get the Fourier transformation as as x of omega e to the power minus j omega t0. So this is the multiplying factor. Actually, if we talk about the xt and if we get the Fourier transformation of xt is capital X of omega, and if we shift the time backward by t0 time, then we will get x of omega e to the power j omega t0. Actually, this e to the power minus j omega t0 is the multiplying factor here. That means if we shift backward the time, then you have to multiply the exponentially decaying function into the Fourier transformed response. Okay, in case of the frequency domain. This is for minus t0 time, and we are multiplying here minus j omega t0. Okay, this is the formula. This is the property of time shifting property.
এটা কি কনস্ট্যান্ট e to the power j omega t0 টা মানে ইন্টিগ্রেট না করে বের করে নিলাম?
Yes, because your t0 is constant in nature, because t0 may be a kind of 2 second, 3 second, 4 second, whatever it may be, right? In the practical domain, and omega is the angular frequency of the signal, that is also the constant, which is twice pi by a, right? So twice pi by t. So if we got the frequency in hertz, then we will get the angular frequency, and j is under root minus 1. So therefore this term is constant in nature. And we will see if we delay the signal by t0 unit by what t0 second, then we will get the Fourier transform x omega e to the power minus j omega t0. Okay, so this is a modulation in frequency. In case of our communication technology, we can, yes.
So the time shifting, the modulation of frequency shifting. So why it is needed?
Yes, pardon. Your voice is not audible properly.
So why
Yes.
the modulation? Why time shifting is needed for Fourier transformation?
Okay, why time shifting is needed for Fourier transformation? Okay. Okay, if we talk about actually signal and system are very much dependent on each other, right? Which we have discussed in our earlier classes. So if we talk about any system which is dependent on previous inputs, right? And many more examples are here in our practical life, that in case of any system, the output which is dependent on past input also, right? So past input means the input signal is delayed in nature, right? Actually xt plus x of t minus 1 or t minus 2, something like that, right? So if we find out the frequency response of that particular type of systems, then their time shifting is very much used, right?
So time is recovery of delay. Or modulation.
Time shifting is a kind of delay. Is a kind of delay. Yes. Yes, a delay. That may be 1 second delay, 2 second delay, 3 second delay. Therefore, the mathematical representation will be like x of t minus 1, x of t minus 2, x of t minus 3, and so on, like this. So that will 1 second delay, 2 second delay, 3 second delay. So, okay. Yes, this is the Fourier transformation, and if we talk about the digital design, and in the next module we will talk about the G transform, Z transform. Okay, in case of Z transform, you will see properly how the delay block plays a vital role in system design. Okay, a delay block in case of digital design. Okay, anyway, we will discuss about it in the further classes. Okay, so this is the time shifting property. And now come to the frequency shifting. Actually, this was time shifting in time domain for xt, and now we will see the frequency shifting for frequency domain. That means here you can understand it better. Capital X omega minus omega 0, that is shifted backward, obviously. So what is happening here? So if we multiply the original signal by e to the power j omega 0 t, right? J omega 0 t. Omega 0 is the prime factor here. So if we multiply it with exponential j omega 0 t, then the frequency will be shifted backward. Okay, so this is also we can prove also, but this is the thing you must remember this. I mean, this is very much similar to the time shifting also. And if we want to shift the frequency, then we must multiply the original signal xt by e to the power j omega 0 t. If we multiply by this exponential function, then the frequency will be shifted in frequency domain. Okay. So this is the thing. And now come to the another one property, which is time scaling. Right. So that is time scaling. Time scaling property is very interesting and very much used in many practical aspects of engineering discipline. Now come to the time scaling property. The Fourier transformation of xt is capital X of omega, and if we take the Fourier transform of capital x of at, I mean the time is scaled by a, the multiplicand, and time is converted into at. Okay, I mean t with some scalar a. So if we take the Fourier transform of this signal, then we will get 1 by a capital X omega by a. Okay, obviously is greater than 0, is positive. So this is another one formulation, or you can say this is another one property of Fourier transformation, the time scaling. Okay, so respond. Okay, let's come into the proof. Actually, how can we get this formula? Okay, it is a simple proof. You may say the capital X tilde omega is equal to minus infinity plus infinity small x at e to the power j omega t dt, right? So x at, okay, let's say at is equal to t tilde. Therefore, dt is equal to 1 by a dt tilde. If we substitute at by t tilde, then this form, we will see this type of form. Actually, this form will come up into our calculation. So x t tilde e to the power j omega t tilde by a into 1 by a dt tilde, and that is simply 1 by a capital X of omega by a. Okay, so this is the thing, and this is very easy to prove that the time scaling property, that is, if the t is scaled by a and the Fourier transformation of x of at, that would be equal to 1 by a capital X of omega by a, where a is positive. This is the time scaling property. Okay, now we will see the time reversal property. Time reversal. I mean, if t is getting negative, then what will happen in the frequency domain? The frequency will also be getting negative. Actually, if t is getting negative, then the Fourier transformation of x of minus t will be capital X of minus omega. Okay. So, and the another one property is, yes, the duality or symmetry. This is very important property in Fourier transformation. Very, very important property, duality or symmetry, and this is very much used in many more cases in communication technology or information science, whatever it may be. Is very much used. Okay, the duality or symmetry property of Fourier transformation. Okay, we will talk about it. Yes, if anyone do not understand the duality or symmetry property, please ask me. Okay, please do not keep in silent mode. If you do not understand, please ask me wherever it is necessary. Okay, so let's discuss about the duality and symmetry property. It is very much actually this is very much actually this is not very much easy actually. Yes, this is duality property, but it is very much difficult to understand what is duality and symmetry property. But it is very much used also, obviously, in many more communication technology and information science. So, the Fourier transformation of xt is capital X of omega. Therefore, the xt is equal to 1 by twice pi minus omega to plus omega capital X omega e to the power j omega t. This is our inverse Fourier transform definition. Okay, sorry, here dt I have made a mistake. Here d omega would be here. Okay, not dt. Okay, please correct it when you will do it yourself. 1 by twice pi minus omega to plus omega capital X omega e to the power j omega t d omega. Okay, if we interchange t and omega, that means if we substitute t by omega and omega by t, then we will see small x of omega, after t is substituted by omega. That means small x of omega is equal to 1 by twice pi minus infinity to plus infinity capital X t, that means omega is shifted by t into e to the power j omega t dt. Okay, j omega t dt. Omega is shifted by t and t is switched by omega. And x of minus omega equal to, actually is if we shift the omega by minus omega, then what will happen? X of minus omega will be equal to 1 by twice pi minus omega to minus infinity plus infinity capital X t e to the power minus j omega t dt. Fine. So if we multiply twice pi to the both side, then twice pi x of minus omega equal to minus infinity plus infinity capital X t to the power minus j omega t dt, and this expression is our Fourier transform of xt, capital X t, right? So therefore the Fourier transform of capital X t, is twice pi small x of minus omega. Okay, twice pi x of minus omega capital X t here equal to sign would not be here. X t with the both imply sign would be here. I mean the Fourier transform of capital X t would be twice pi x of minus omega. And here we have seen the Fourier transform of xt is capital X of omega. Okay, look at this formula. and then look at this formula. Capital X of t, the Fourier transform of capital X of t is equal to twice by small x of minus omega, right? So this is the thing. This is the duality property, and this is very much applicable in many more cases. Okay, let me discuss in detail. Uh, let's come into this one. And if we see this example, this will be clear. Okay, let's recalculate again the duality property. Xt is equal to 1 by twice pi, and this expression minus infinity to plus infinity capital X of omega divided by j omega t omega. And if we replace t by minus t, and then the expression will be changed into this formula. And if we interchange t and omega, then we will see small x of minus omega is equal to 1 by twice pi minus infinity to plus infinity capital X t to the minus omega dt. And this expression is the Fourier transform of capital Xt. Okay, so the Fourier transform of capital Xt, the Fourier transform of capital Xt is equal to twice by x of minus omega. Now let's see the two expression. The first expression is twice by x of minus omega. Both implies xt. That means if we take the Fourier transform of capital Xt, then we will get twice by x of minus omega. And if we take the Fourier transform of small xt, then we will get the Fourier transform capital X of omega. Okay, so how this is possible? This is very much puzzled actually. Let's look into a particular example. Okay, if we talk about the rectangular function, okay, this is the rectangular function in time domain. Suppose this is xt. Let's say xt, and here minus tau by 2, and the amplitude is 1. Fine. If we take the Fourier transform, yes, now this is clear. Yes, if we take the Fourier transform of this rectangular function, then we will see the Fourier transform function will be like this. That means this is our capital X of omega. This is a kind of sinc function. Okay, just forget about this sinc function. And if we take the Fourier transform of this type of signal, we will get this expression or this representation, this graphical representation. Now, let's come into this type of signal in time domain, right? This is the capital X of t. Just we replace omega by t. Okay, this is time axis, and this is your omega axis, and here this is your time axis. And if we take the Fourier transform of this expression, we will get this expression, which is very much similar in nature with this form, right? So the theory is that if the Fourier transform of xt is capital X of omega, then the Fourier transform of capital Xt, the Fourier transform, again I am repeating, the Fourier transform of capital Xt will be twice by x of minus omega. Okay, so if we take the Fourier transform of this expression, we will get this kind of rectangular form, this kind of rectangular graphics, where the omega axis, the interval, the points of the omega axis is minus tau by t2 plus tau by 2, and the amplitude is scaled by twice pi, right? The amplitude is scaled by twice pi here. That means we shift 1 by twice pi. The amplitude is getting increased by twice pi. right? So, and the omega is the frequency reversed form. If we take the reverse of this expression, we'll get the same expression, that is minus tau by 2 to tau by 2, because this is even in nature, even signal, right? This is our even signal. If we take x of minus t, we will get the same expression. We will get the same representation, right? So this is the duality property. This is the example of the duality property, right? So if we take the Fourier transform of this rectangular expression, we will get this kind of sinc function. And if we take the Fourier transform of the sinc function in time domain, we will get the rectangular function. Okay, this is the duality or similarity property. But one thing is to be noted: the frequency response. If we take the Fourier transform of the sinc function, the frequency response is scaled by twice pi or is multiplied by twice pi, and the frequency is getting reversed. Okay, so as this is even signal, nothing is being happened to the frequency reversal form. Okay, so the frequency reversal form is very much similar to the time reversal form. Okay, only thing is that the amplitude is scaled or increased by twice pi. Okay, in here the amplitude was 1, and here in this case the amplitude is twice pi. Okay, so this is the thing, this is the duality property. You must be thinking about it very deeply so that you can understand the duality property, because this duality property is very much used in many more cases, in many more applications. Okay. Let's come into the Fourier transform of impulse signal. If we take the Fourier transform of impulse signal, then we get 1. That means the Fourier transform of impulse signal is 1. And if I mean, according to the time shifting property, that means the Fourier transform of delta t minus t0, that would be 1 into e to the power minus j omega t0, right? Which we have seen in our previous discussion or in previous document, that if we shift the time by t0, then we have to multiply by exponential form in frequency domain. And if therefore the capital XT, if the capital XT is equal to e to the power minus j t0, then the Fourier transformation of e to the power minus j t0 would be twice by x of minus omega, and that is equal to twice by delta of minus omega minus t0. Okay, this is minus omega minus t0. This is also the frequency shifting property. Okay, this comes from the frequency shifting property. If we multiply by this exponential form, then frequency will be shifted by t0. Okay, so this is equal to twice by delta of omega plus t0, as because delta of minus omega minus t0 is equivalent. Delta of minus omega minus t0 is equivalent to delta of omega plus t0. These two signals are similar in nature. Okay, I mean, that means omega is equal to what? Omega is equal to minus T0. Here also omega is equal to minus T0. Okay. So this is the thing, and then we have got that the Fourier transformation of e to the power minus jt t0 is equal to twice by delta t omega plus t0. Now, if we substitute t0 by omega 0, if we substitute t0 by minus omega 0, then what we will see? We will see the Fourier transformation of e to the power j omega 0 t, e to the power j omega 0 t is equal to twice by delta omega minus omega 0. Okay. So the Fourier transformation of e to the power j omega 0 t will be twice by delta omega minus omega 0, right? So that means if we repeat again, the Fourier transform of delta t is equal to 1. If we shift the time by t0, then we will get this expression. If we multiply the signal by exponential function, then we will get the frequency shift, which is twice by delta omega plus t0 here. And now if we substitute the t0 by minus omega 0, then we will get twice by delta omega minus omega 0. Okay. So this is the thing actually which is being used, or which will be used to get the Fourier transformation of the sine signal and cosine signal, as the sine signal and cosine signal can be decomposed into the exponential functions. That is, the cosine signal is equal to cosine of theta is equal to cos theta plus j sine theta by 2, and in case of your sine signal, sine theta is equal to e to the power j theta minus e to the power minus j theta by twice j. Right.
So can you explain the last part again? Like from delta t, Fourier transform of delta t equals to 1.
Okay. Yes, sure. Yes, the Fourier transformation of delta t is equal to 1. Okay, which we have seen in the previous in your previous document. And if we shift the delta t, the t by t0, if we delay by t0, then we have to multiply e to the power minus j omega t0, right, with the 1. That means the Fourier transformation of delta t minus t0 would be 1 into e to the power minus j omega t0, right? This is the thing. Now the Fourier transformation, this is your xt and this is your x omega. Okay, this is your xt and this is your x omega. Now, if the duality property is applied here, then the capital XT, I mean the Fourier transformation of capital XT will be equal to e to the power minus jt t0. Okay, if duality property is applied here, therefore the Fourier transformation of this signal, the Fourier transformation of e to the power jtt0, the Fourier transformation of e to the power jtt0 equal to twice by x of minus omega. Okay, twice by x of minus omega, and that is equal to twice by delta minus of omega minus t0. As we can see, this is one kind of shifting property, the frequency shifting. If we multiply any original signal by any exponential function e to the power minus jtt0, then the frequency will be shifted, right, twice by delta minus omega minus t0. That means the frequency is being shifted by T0. Okay. So that is equal to twice by delta omega plus T0, as delta minus omega minus T0 is equivalent to delta omega plus T0. Okay, there is no discrepancy. Delta minus omega minus T0 and delta omega plus T0. So now if we switch T0, by minus omega 0, then the Fourier transformation of e to the power j is remain intact and t is remain intact. We switch T0 by minus omega 0. That means this expression will be come into the form e to the power j omega 0 t. Therefore, the Fourier transformation of e to the power j omega 0 t would be twice by delta omega minus omega 0. That means here also t will be shifted by minus omega 0. Right. So this is the thing. That means the Fourier transformation of e to the power j omega 0 t, the Fourier transformation of e to the power j omega 0 t would be twice by delta omega minus omega 0. Okay, this is the thing. Nothing more than that. Here, two properties has been applied. One is duality property, and another one is time shifting, and another one is frequency shifting property. These three properties are applied here, and finally we have got this. Okay. And now it's clear to you. Here, three properties are applied here. Nothing more than that. The duality, the frequency shifting, and the time shifting. If we apply these three properties onto the delta function, then we will finally get this function. Now it's clear to you?
Yes, sir.
Yes, sir.
Okay. Okay, thank you very much. Okay, now come to the differentiation. Okay, if we take the differentiation of the function in time domain, then what will happen in frequency domain? So if we take this one, then 1 by twice pi minus infinity. This is the inverse Fourier transform, right? So that is 1 by twice pi minus infinity plus infinity d dt of capital X of omega into e to the power j omega t d omega. Okay, that is 1 by twice pi minus plus infinity. This is capital X of omega, and if we take the d dt, this is the function of omega. This is independent of time. So we only take this one. Okay, this function, and if we take the differentiation of this function, then we will see j omega e to the power j omega t d omega, right? So, and finally we will see this is the Fourier inverse. Okay, this is the Fourier inverse of capital X omega j omega. Therefore, we can say the Fourier transform of this expression will be this one, capital X omega j omega. Therefore, if we take the differentiation in your time domain, then in case of frequency domain, the multiplicand will be j omega. Okay, the multiplicand will be j omega. Okay, for capital X of omega. And if we multiply jt in time domain, then we have to differentiate in frequency domain for the original signal. And if we talk about the integration minus infinity to t x tau d tau, if we take the Fourier transform of this integration, then we will get pi small x of 0, I mean x, the value of the function at t is equal to 0, delta omega plus 1 by j omega capital X of omega. Okay. So yes, so this is the thing which we have learned today, and yes, let me summarize. We will discuss about the convolution in next lecture. Mm,
স্যার ডিফারেন্সিয়েশনের স্লাইডটা আরেকবার ওপেন করবেন, একটা জিনিস জাস্ট লেখা বাকি আছে, জাস্ট লাস্ট লাইন।
okay, yes.
হ্যাঁ স্যার, ডান ডান, হয়ে গেছে, থ্যাংক ইউ।
Okay, so you people are noting it down. I mean, you people are writing what I have just shown you. I mean, this kind of PDF you are writing it down in your copy or your notebook.
স্যার কিছু কিছু পয়েন্টস লিখছি, সব কিছু লিখছি না।
Okay, that's good.
স্যার এই পিডিএফটা যদি আজকে পাঠিয়ে দেন তো ভালো হয়।
Okay, this PDF. Okay, I will share this PDF with your CR, I mean, with Rahul and Isa, and they will distribute or deploy with you all.
আচ্ছা, থ্যাংক ইউ স্যার।
Okay, so yes, I think the previous notes has been provided to all of you. The previous note. Have you got this?
Yes, sir.
Okay, thank you. Okay, so yes, in this class we are talking about the Fourier transformation of the unit impulse in exponential form, and we have taken an exceptional example which is unit step. Unit step signal is not absolutely integrable, but we will get the Fourier transformation value of the unit step signal, and that is equal to pi delta t plus 1 by j omega. We will see this proof in our later lecture, and then we have talked about the linearity property. This is very much easy. Then we have talked about the time shifting property. If we shift the time by t0 in frequency domain, we have to multiply by e to the power minus j omega t0. Then we have talked about the frequency shifting property. If we what can I say? If we multiply e to the power j omega t0, then the frequency will be shifted. Right? The frequency will be shifted. That is omega minus omega 0. And then we have talked about the time scaling property. If the t is being converted into AT, then in this frequency domain, the amplitude is scaled by 1 by A, and the frequency is scaled by 1 by A. Okay, is omega by A. A is greater than A is positive, and this is the proof. You may understand it very easily. Then time reversal property, and then we have talked about the duality or symmetry property, and we have taken two graphs also here, the two graphs where we can better understand the physics behind the duality property and what is the physical phenomenon, or you can say what is the graphical representation of the duality property. And this is your time domain signal. Take the Fourier transformation, we will get this function. And again, if we express this function in time domain, and if we take the Fourier transformation, then we will get this expression. This is interchangeable, you can say. Only one thing is that the amplitude is scaled by twice pi and the frequency is reversed in nature. This is the thing. And this is the duality property. The xt, I mean, if the frequency transformation of xt is capital X omega, then the frequency transformation of capital xt would be twice pi small x of minus omega. And using this duality and time shifting and frequency shifting property, we have got this expression. I mean, the frequency, what can I say? The frequency response, sorry, the frequency transformation of Fourier transformation of e to the power j omega t of e to the power j omega t is equal to twice pi delta omega minus omega 0, right? So here delta t, the frequency transformation of delta t is equal to 1. Now we have taken the time shifting property. We have got this one. Let's say this is x of omega and this is x of t. And now we apply the duality property. That means if here omega is equal to t, okay, if here omega is equal to t, then this will be twice pi, this will be twice pi into delta into here your frequency reverse form, okay, frequency reverse form. Frequency reverse form means minus omega minus t0. Okay, this is the thing actually. Just look into this. Omega is being changed by t. Okay, this is your capital X of omega. This is small xt. This omega is replaced by small t. So that would be e to the power j small t t0. This is this one. E to the power minus j small t and t0, small t t0. And the Fourier transformation of this one will be twice pi x of minus omega. This is the formula. Okay, this is the formula. Twice pi x of minus omega. So x of omega, x of here twice pi is constant and small x of minus omega, that would be delta of minus omega minus 2 minus omega minus t0, right? The t is being replaced by minus omega, and that will be equal to twice pi delta omega plus t0. Fine. So therefore, if we replace t0 by omega 0, then we will get this expression. And finally, we have got the frequency response of this exponential form will be twice pi delta omega minus omega 0. Right? So this is the thing. And this is very much important property, you know. This is very, I mean, this is very important property. I mean, to express the sine signal and cosine signal. Okay. To express the Fourier transformation of sine signal and cosine signal. Okay. This would be used when we will try to get the Fourier transformation of sinusoidal signals. Okay, that may be sine wave and that may be cosine wave, whatever it may be. Okay, so the last one is the differentiation. If we take the differentiation of the time domain signal, then j omega will be the multiplicand of the frequency domain signal. And if we multiply the time domain signal by jt, we have to take the derivative of the frequency transformed signal, okay, in Fourier domain. And if we take the integration of the time domain signal, then we will get this type of expression in your frequency domain. So this is all for today's class. Okay, if you do not understand anything, then please ask me. Okay, in my next class or in the further class, if you face any kind of trouble or any kind of difficulties to understand the calculations or the mathematics, then you may please ask me. Okay. So, yes, this is the thing. Now, I think this equation has been clear to you. Any one of you has asked me about the delta t function and how this expression has come up with this formulation. Now it's clear to you. Now, is it clear to all of you that the Fourier transformation of e to the power j omega t is twice by delta omega minus omega 0?
Yes, sir.
Okay. Okay, thank you very much. Then if you do not have any question, then I will leave now. Okay, thank you very much.
Thank you, sir.